the non-isothermal flows. So the last 2 or 3 times we talk about non-isothermal flows in settings such as a thin straight pipe and a lubrication setting. And today I'll talk a bit about something that is more interesting from the practical point of view, the curved thin domains. So put like this. So non-isothermal flow. In a curved pipe. And we will mostly focus on the geometry of the domain, basically, since this is a special type of curved domain. I'd like to describe it if you haven't seen it up till now. And I will describe also the special frame for a more general curved domain. So let's put like this. Geometry. Okay, so what we will consider is a thin pipe which is of helicoidal shape. So we consider so of course you want to be as general as possible. So here we are considering a 3-dimensional pipe. So 3-dimensional thin pipe. So of helical shape, which is very commonly found in the various applications. With the central curve of the pipe. So we have a specific parameterization for this. So you put this way R epsilon is x1I plus a cosine of x1 over epsilon. So this is needed. Y plus a sinus. Where of course x1 goes from 0 to L and a is strictly positive. So basically I have something like this. So this is of order epsilon, and the thickness of the pipe is of order epsilon. So thickness of the pipe is of order epsilon. But more than that, you also have the distance. So the distance between the spirals is also epsilon. Of course, the basic idea that I will go through is that when you have a problem posed in this kind of domain, in some way you need to change your problem to be in the setting of a thin straight pipe. So this is what we will do. Of course, this is not necessarily so easy. It can be quite tedious, and the calculations are quite tedious. So in this specific case, we have this curvature or flexion will be of order 1, and the torsion will be of order epsilon. I will later define these, so this is torsion. In a classical curved pipe, which doesn't have these kinds of spirals of order epsilon, both are of order 1. Okay, so what do you do? Well, for start, you need to introduce the corresponding basis since you have this curvature. So we can work with the Fermat basis. So you have the following. The epsilon of x1 is we defined this r epsilon. It was the parameterization, of the central curve over r epsilon x1. So we can more or less easily compute this. I will not write this down. You can check it. I will write at the end here. We are following basically 2 papers, so I will write them down by Professor Pajanin and other authors. So this is the tangent. Then you have this. So this is more or less classical. You have the tangent normal and B normal. This is the normal. Here I think you also need this. And B epsilon. And of course, this is perpendicular to both. So they all depend on x1, of course. So for starters, you have this classical Fermat basis. And what do you do? Well, as I mentioned, you somehow need to transfer your problem from this helicoidal domain to a thin straight pipe. So this is, there's a procedure to this. So you define, for example, S epsilon as a thin straight pipe. So you have x1, x2, x3. Have x1, of course, which goes from 0 to L, and x2, x3. Is from epsilon b. So I won't, this notation is now, we saw a couple of papers, more or less standard, so I will not write each time when I write b or something like this. You know what it means. So we define this big phi by goes from S epsilon to R3. So in the following way. So you have R epsilon of x1 plus x2 and epsilon of x1 plus x3 b epsilon of x1. Okay. And your domain will basically be given in this way. So in this way, you write down the relation between your thin curved domain and the straight pipe via this big phi. Okay, so this is more or less classical, but I would like to mention also, as I said, a more general framework where we use the so-called Germanos reference system. Maybe you heard about it, maybe not. You'll see now. So let's say remark 1. Okay, so this is one way you can do it. However, if you have a general curved pipe, you define it in a similar way, but there are some differences. So it's defined in a similar way. Okay, so if you take gamma to be a generic curve, there are a number of papers that use this framework, so I think it's not bad for you to see it. So let gamma be a generic curve in R3. So it's parameterized by its arc length. Of course, x1 from 0 to L, and let's so we denote by pi. This is more or less classical, which needs to be of class C3 for different reasons, not to go into technicalities. From 0 to L to R3. So let this be its natural parameterization. Of course, such that its derivative in each x1 is different than 0. Okay, so these are the basic terms, and what you do now is the following. So as I mentioned before, I spoke about flexion and torsion, so we define them in the following way. So kappa of x1 is the double derivative of p of x1. So this is flexion, also known as curvature. Then you have torsion, which is defined in the following way. So these are basic elements of differential geometry. Definitely, we don't go much into maybe deep into the differential geometry, but we need this in order to basically compute the first order correctors, etc. So basically the technical side. So minus b x1. This is torsion, and you have tangent, which is given this way, normal, and b normal. And now what do you do? Well, you introduce this Germanos reference frame. So it was used in a number of papers. I also used it in my PhD to compute some things regarding micropole flow in a curved pipe. So it was introduced by Germano, I think in 1982. to investigate these effects of flexion and torsion, and it has its advantages. So we have this n alpha of x1. So it's given in this way. Cosine of alpha of x1 n of x1 plus sine of alpha of x1 here you have minus sine of alpha this alpha of x1 is for technical reasons defined in this way. So minus x0, x1, the torsion, plus some alpha 0. So basically we have that the derivative of alpha is minus the torsion. Okay, so this is quite, I will not say widely used, but it's often used. So I think it's good for you to see it. And of course, in a similar way, we now defined the relation between the thin straight pipe and the curved pipe. So this is in the more general framework. So, for example, we can denote it with phi alpha from S epsilon to R3. So in the following way. Pi of x1 plus x2 and alpha of x1 okay, and of course your domain will be obtained as before. So here you have this P epsilon. It's a thin curved pipe obtained via this phi alpha from the thin straight pipe. Okay, so these are some basic ideas. Today I'll just focus in basically on this framework in order to, it's not so trivial to go from, to write down, if the equations are written down in the thin curved pipe, to transfer it to the equations written down in the thin straight pipe. In 2 dimensions, okay, there's also a lot of trouble, but in 3 there's really a lot of work to be done, and it's quite painful. But it is as it is. Okay, so I know that here but the good news is, since people don't like to do these kind of things, there's always open problems you can address. Okay, are there any questions regarding this? Or?
Should be just a mathematical one. If you can't, say, you basically stretch the curved pipe. So you need some good structure for everything. But if you don't have this structure, is it possible to keep going? I should say that it's possible, but
what do you mean if the like if the curvature is too like rigid, or what do you mean?
Yes, you can't make it straight or something like that.
I was asked a question, I think, by Professor Tambacha, if this can work. Is just a second. There are some limitations, yeah. For example, if this, okay, maybe if you have curved pipe, but then here you have like this. You mean like this?
Yeah.
Yeah, I think you can't, because it needs to be smooth enough. I'm not sure about the technicalities, but definitely, yeah, because sometimes in numerics you have problems like this, right?
Yes, that's why.
No, it can't work.
Yes.
I think no. I think he's.
Of course, by parts, it's if you look at it at each section, you
Yeah.
can transform each section.
No, but this is a problem, of course.
This is the junction.
Yeah, he told me some way. I think maybe some regularization, but I'm not sure how they address it. And probably they like cut it off here,
Yes.
and then considered maybe this special. I'm not sure, but yeah, you can't, unfortunately. Yeah, it's a problem. So you have, I think the curvature needs to be at least of class C2 or something.
Yes, usually, yes.
Not sure. Yeah. Okay, any more questions? Okay, so basically this, what I'm talking about today, is from two papers. The first one is from Špaloka. So this is a paper on the effects of curved geometry on heat conduction through a sorted pipe. So it's from nonlinear analysis, real-world applications from 2010. And the other one is same author, so modeling of heat transfer in a laminar flow through a helical pipe. So mathematical and computer modeling from 2009. Okay, so these are the main references. So I would like to talk a bit about the equations. So let's see how you can transfer the problem from the curved pipe to the straight pipe. So 3, 4, 2. So equations and boundary conditions. Okay, so as I mentioned, so I basically talked about the domain, but of course we will talk still about non-isothermal flows, at least for today. So we consider the non-isothermal fluid flow. As I mentioned, in a helicoidal pipe, sorry. So I wrote down the heat equation a number of times, so let's recap. So the heat equation reads, so I have minus k Laplace of the epsilon plus rho 0 Cp okay. However, this, as I think the previous paper also had this setting, so this u epsilon is known and was computed in a different paper, so this velocity is known. So where the velocity is known, and limited in the following. So basically, again, you don't have a nonlinear problem. The problem gets linearized. So and fluid flow through a helical pipe. So it's in ZAMP 2007, if you're interested. So regarding the boundary conditions, they're more or less classical. However, it will be quite more complicated since you will need to write them in a straight pipe. So we assume the following boundary conditions. So on the lateral boundary, we have this classical cooling condition. This knee is the external outer normal. So alpha epsilon g, so this needs to be Euler epsilon minus T epsilon. On the lateral boundary, and T epsilon is Ti on the ends of the pipe. Okay, so as I mentioned, you need to write this problem in the straight pipe. So for this, you need some more elements of differential geometry. Part of this framework was taken from the appendix written by Professor Tambacha in Professor Radulović's book, Uvod u rubne zadaće mehanike kontinuuma. I don't know how to translate. So this was Radulović. So differential operators, this is in the appendix. So this was appendix. Okay, so it's written nicely there. So what you need for starters, there are a lot of these small technicalities. You need to understand the notation. So you have the Einstein summation, which is perhaps a little maybe strange if you haven't seen it, but it's classical. So this VI, this will be the Christophel symbols. So this basically means summation from 1 to 3, in our case, VI. So if you see something like this and you're confused, this basically means this. This is more or less classical in differential geometry. Okay, so in order to transfer my problem, I need to explain, to introduce the covariant, contravariant basis, and the Christophel symbols, and then write the operators in curvilinear coordinates. So basically I have this covariant basis. So regarding the covariant basis, what the elements are given as the following. So is a derivative of big phi over the x1. So what do you obtain? Well, you obtain free vectors in this form. So x2 minus a over epsilon, e epsilon of x1. Okay, and this an epsilon of x1 plus I. And as you can see, this a1 will be of order 1 over epsilon. Okay, regarding the other two. I will not write, of course, all the technicalities down, since it would take a lot of time. These are just the basic ideas, in case you haven't seen them or want to recap a bit. So, a2 of x is an epsilon of x, and a3 of x is epsilon over the square root of a squared plus epsilon squared, e epsilon plus a over square root of a squared plus epsilon squared. Okay, this can be more or less easily obtained when you know this relation for the elements of the covariant basis, sorry. And this e epsilon of x1 is 0 sine of x1 over epsilon, and the minus cosine of x1 over epsilon. So we have the basis. So e epsilon and epsilon and I. Okay, so this is the first element you need in order to write your operators. So covariant basis, the contravariant basis is what you can assume. So contravariant basis. So you have only the indices go in the upper part. So basically what you have is when you multiply elements of covariant and contravariant basis, it is equal to the Kronecker symbol. Okay, and also you need to introduce.
Maybe it should be emphasized. See this
Sorry.
This first vector of covariant basis is a 1 over epsilon. So here he writes, he treats the helical setting. It doesn't enter in this general framework. And why? Because here we treat the specific helicoidal pipe that eventually appear in the application, in which the distance between two coils of the helix are of the same small order as the pipe's thickness. Okay? And due to this epsilon that is essentially introduced in the central curve of the pipe, then this vector of covariant basis is of order 1 over epsilon, and you cannot anymore use the standard Kronecker basis for writing the differential operators, but you need to modify this basis by introducing this another basis that we brought.
Yeah, thank you for the remark. Okay, so besides this contravariant and covariant basis, as I mentioned, you need to introduce this so-called Christophel's symbols. So denoted in this way. Gamma I yacht k is given in this form. An important property of these symbols is they are symmetric in lower indices. So we have this kind of symmetry. So in case one day you'll be computing in these curvilinear coordinates, that you know some of these properties. It's useful. Okay, and you know this in the following way. So this gamma I is basically this matrix. So there holds the following. So the gradient of big phi of epsilon. So this is basically the elements of the covariant basis in columns. So A1, A2, A3. And on the other hand, as is expected from the relation between the elements of covariant and contravariant basis, this inverse of the gradient of phi will be given in this form. So the elements of the contravariant basis will be rows here. So A2 and A3. Okay, so these are some very basic things that you need to know in order to write down the operators. So here we do not have, fortunately, too many operators to deal with. Basically, you have the Laplace and the gradient. Okay, so you don't have, I don't know, rotation, divergence, etc. So you can write it down in this way. I'll write down the whole formulation. So if you want to transfer your problem to a thin straight pipe, you have this relation. So it's a bit complex. So it's gradient of. So this is given in this form. So this theta will be defined on the temperature defined on the straight pipe. So minus, I will write this down. Gamma 1.
So this appendix that Marco mentioned, it's in the book of Radulović, and it's very nice because there you can find each differential operator that you will ever need with the curvilinear coordinates. Based on these formulas and the approach we developed many years ago, we are able to write any equation in any basis that is suitable for the further analysis. Because here, due to this specific geometry of the line, we need to write the equations in different bases that does not depend on small parameter epsilon in an unconvenient way. And we know how to do that based on this formula and this.
Yes, as Professor Pardin mentioned, this is very useful. So regarding this problem, as I mentioned, you don't have that much problems. You basically need to write down this Laplace operator. Of course, this usually, okay, in this setting, maybe not so much. Sometimes you obtain very, very complex, complicated equations, so it's a lot of work to go through them. So since we want to write everything, in a straight pipe. We also need to transfer the gradient. So fortunately, this relation is more simple. So it's given in this form. Okay, so the relation between, just a second, sorry. So this theta epsilon is basically the temperature in the straight pipe, which is appearing over here. Okay, so once you have this, these two operators, basically you can write your, so we can now write the heat equation in a straight pipe. So as I mentioned, as expected, there's a bit of computation here, and you obtain, of course, a more complex system of equations. So, sorry, a more complex equation. So minus k two times derivative over x2 of this theta. So I'll write down the whole thing so that you have a feel of it. So minus 1 over a. There are quite a bit of new terms that appear. Of course, all this was also in the paper I mentioned, so fluid flow in a helical pipe. It was done for the corresponding equation for the velocity and pressure, which are well known. So there's also a lot of work to do there. And then when that velocity was computed, it was just plugged in here. So minus 3x2 squared minus epsilon squared over a squared. Okay, so this is only the first part. Okay, plus epsilon over A. So here you have, this comes from the nonlinear term, which is basically now linearized since this u epsilon is known. So this u epsilon 1 was written in these papers in the appendix, but as I mentioned, it was originally computed in the paper from Zamp. So plus minus x2 squared. Okay, so as you can see, it's a bit more complex than the original equation, but you can work with this. So in the zero order approximation, actually, we will not do this today. You can check in the paper. But actually, I think in the first 2 or 3 terms, so in the zero-order approximation, first-order corrector, in second-order corrector, there are not many terms that appear. But in order, I mean, the procedure is classical regarding the heat equation. We saw it, I'm not sure last time or the time before that. You will write down in this particular example, after you plug in the asymptotic expansions, the basic equations for the first 5 or 6 correctors, the zero-order approximation, I think, and the 5 correctors, and you will compute you'll obtain basically the second-order ODEs for the zero-order approximation first, second-order corrector from the corresponding compatibility conditions. I think the third or the fourth, fifth, and sixth, something like that. So you need to go quite further if you want better approximations. But this is more or less very similar to what I have already considered in a thin straight pipe, so I will not talk about that. But just that you have a sense of what is happening. So this is in S epsilon. Okay.
Here we only write the terms for order epsilon squared, and we left the lower order terms.
Yes.
And this approach, when one wants to deal with only the thermal flows, first focus on the thermodynamic part is quite complicated. Because first we want to attack the linear part. So here we assume that the velocity is given, making the heat equation linear. Of course, aim is always to consider a couple of things. So the thermodynamic part and the thermodynamic. This is always like the first step. And if you notice in the heat equation, on the right-hand side you have 0. You can complicate this equation by adding some terms coming from the viscous dissipation effects on the right-hand side of the heat equation. But then the problem becomes nonlinear. But it's also a
Okay. Since I don't have much more, I think I will not make a break. I will just finish this up. So I would just like to mention here, of course, this U epsilon is small U epsilon. So this is just the notation.
This epsilon in this equation are due to the epsilon from the central part. So still this x2, x3 are ordered are the cross-sectional elements. So it depends on the epsilon.
Okay, so in order to somehow fully set your problem, you need to transfer the boundary conditions, the cooling condition to this string pipe setting also. So we need to write the cooling condition. In much the same way. So this lateral boundary can be written in this form. So epsilon x1 plus this epsilon cosine of phi and epsilon of x1 plus epsilon sine of phi be epsilon x1. So x1 is from 0 to L, and phi is from. Okay, so to write down the cooling condition, you need to introduce the basis for the tangential space. So So we write down the following. So we denote it in the following way: T epsilon 1, T epsilon 2. And now this external normal is given in this way. So T epsilon Okay, so now you can compute it. It's some complex term plus something which is of order epsilon to the third. And once you have this, you can write down your cooling condition in the following way. So it's K over epsilon x2 derivative over x2 plus x3 minus K over A epsilon x2 squared x2 plus x2 x3 Okay, as you can notice, there are again quite a bit of new terms that appear. But it's not too complex, but you need to be careful when you're writing down this condition. Okay, minus K epsilon x3 over A squared, the epsilon over x1, minus d theta epsilon over x3 is alpha epsilon g minus theta epsilon. So this is the complete cooling condition, and it's given in 0L times epsilon times the boundary. Okay, so basically this is the whole setting that you need to introduce. So you introduce the corresponding elements of differential geometry, and using these equations for the transference of the differential operators to write them down in curvilinear coordinates, you can write down your problem in a thin straight pipe. And now the approach is, well, more or less classical. So you do the asymptotic expansion technique. So as we had before, again, you will assume that epsilon, so the leading term is of order 1, so x1, x over epsilon, okay. So you rescale the equations, you plug the expansions in, and as I mentioned, you write down equations for the at least, I think, 5 or 6 order correctors. And from the necessary compatibility conditions, you obtain second order ODEs for the zeroth approximation, first and second order corrector, and compute them. This is basically it. You also have to do a boundary layer analysis, but this is more or less classical since we mentioned that earlier. And regarding the justification, just a comment. 3, 4, 4.
Did you say about heat transfer coefficient? It also depends on the side, yeah? It's alpha.
I'm not sure in this paper it does. Yeah, but
so that's an important remark. When we cooling condition, this Robin boundary condition, then this alpha, the heat transfer coefficient between the exterior medium and the fluid inside the pipe, plays an important role depending on its size. It turns out that always that it should be compared with a small parameter size, and we keep one with the heat domain setting as this one. And then we can identify the critical case when in the effective equations you obtain the effects of, I don't know, this function G is the exterior temperature. So in this critical case, you obtain all the effects that are interesting from a physical point of view. But this alpha it's very important in the thermodynamic setting. So if one considers a thin domain setting, then this heat transfer coefficient should be compared to small parameter psi, because depending on its size, order of magnitude with respect to the small parameter, one obtains different asymptotic models. And always it is the aim to find the most interesting one that captures all the effects. And another thing, we put there epsilon next to G, because we want to simulate the situation when the fluid inside the pipe is cooled by the exterior medium. So the temperature outside of the pipe is smaller than the one. Because this helicoidal pipe naturally appears in the heat exchangers. And in heat exchangers you have a pipe in which the fluid inside is cooled with the surrounding.
Okay, I think the last 2 or 3 lectures we mentioned papers where this was considered. So this different models that you obtain when you compare this alpha to various degrees of psi. Okay, so just regarding this justification, what you basically need to do is you need to adapt. So we need to adapt. So all the technical results. So taking into account the complex geometry of the domain. So the results are maybe a bit more technical, but basically the idea is regarding what we have gone through thus far, basically the same. So you have here Poincaré, and of course you need to have L4 estimates for the nonlinear term. Trace estimates, etc. Okay, so the rest basically is more or less standard. Okay, so this is what I meant to speak a bit about today. Sorry for taking the break. So the basic idea is that you try to memorize a bit about this transference of the problem from the curved pipe to the straight pipe, and then address the problem as if you would in a thin straight pipe, which we did in more detail in the last couple of lectures. Okay, so any questions? Okay. Well, I don't know. I hope that Jean will be able to maybe continue from next week. I will be very glad. So, is there anyone in the audience?
No, but the audience is here.
Okay. Okay, well, anyway, we will probably continue next time with a couple of lectures regarding the unfolding method, and I'm looking forward to it. Thank you for your attention.